All right, so something that's related to collision theory is the transition state theory. Okay? And so what we see when molecules collide is they form what we refer to as a transition state. This is sort of a clustering of atoms that is halfway between the reactants and products. And in that transition state, the atoms that are oriented in a certain way can either go back to reactants or can go on and form products. The other term you may see in terms of, instead of transition state, is activated complex. This means the same thing, but it's basically an unstable grouping of atoms, an unstable molecule. The reaction that I'm showing here is the reaction, the isomerization between methyl isonitrile, that's this one, and the formation of acetonitrile. In this reaction, the only thing that's taking place is we are switching the bonding of this CH3 methyl group. So currently on the methyl isonitrile, it's bonded to the nitrogen, and the acetonitrile, it's bonded to the carbon in the nitrile group. Okay. So this is what we call an isomerization. You're going to see a lot more of isomerization and a lot more of transition states when if you're taking organic. I don't know how many of you are doing that. You also will see sometimes a transition state written with a double dagger. Okay, this one is in brackets. Sometimes you see the brackets plus the double dagger. That just signifies transition state. Okay. So let's take a look at this in a little more detail. Okay. So we have a reaction progress diagram with our potential energy on Y and reaction progress on X. And on this here is our reactant. Have you guys practiced writing these? This is from chapter 5, right? This is from doing enthalpies and things like that. Have you seen a lot of these? Okay. It's been a while. Okay, that's fine. So we'll go over it. And then on the right-hand side, we see our products. The energy between the energy of the reactant and our products, that's the enthalpy for the reaction. Okay. So here we have an exothermic reaction. The energy of the products is less than that of the reactants. The way that it's proposed that this isomerization takes place is kind of neat. What happens is the molecule starts to bend around the nitrogen, and then this carbon begins to interact with the triple bond on the nitrile. And now we have sort of this T formation. Okay. This is theoretical. I don't know that this has ever actually been observed experimentally. There are a number of different experiments that you could do to sort of test this theory, including Fourier transform infrared spectroscopy. It's a form of vibrational spectroscopy where we look at how molecules are vibrating, bonds are vibrating. This would have a different vibration than these two. Okay, so you would be able to see a difference there. In any case, eventually the carbon-carbon bond forms, and the molecule then sort of becomes more linear, and we have our product. The important thing, one other thing that you need to be worried about is E sub A. That's our activation energy. And so that's the difference in energy between the top of the hill and the reactant for the forward reaction. Okay. if we're looking at the activation energy for the reverse reaction, that's the difference between the energy of the products and the top of the hill. Okay? So you will see both of those. I think that shows up in a homework problem. I think it actually shows up in a problem we'll do later, too. The other thing is that at the top of the hill, this is where our activated complex or our transition state exists. Okay, this structure is at the top of the hill. So we're at the top of the hill. Now we can either go back and form reactants or go forward and form products. Okay. So if we have a fast rate, are we going to have a large value or a small value of our rate constant? This is kind of a recall question. Fast rate, large or small k? You guys remember? Large K, yes. Okay. Will that correspond to a large activation energy or a small activation energy? Small, yeah. That one's kind of easier to picture because if we're imagining having to go up the hill, okay, it's going to be faster to go up the short end of the hill than it is to go up the long end of the hill. Okay. So this is small e sub a, small activation energy. Yes?
So will this relationship between like K and activation energy always be inverse?
Yes, and that is, I don't have it right here, but it is based on the Arrhenius equation. Okay. Any other questions? Yes?
Does the CN ever break away from the CH3, or does it just kind of move they're always still
That's a good question. I would imagine if you give the molecule enough energy, it can break away. You can just break this bond. But I think if we stay at a certain level, a certain energy below that, the interaction is going to be something like what's shown in the transition state. Yeah. Yes?
once they're at the top of the hill,
Yeah.
what determines whether the reactants form product or whether?
Probability. Yeah. Any other questions? Back and recall that we said a fast rate is a large K. Cool. Okay, another quick question here. Is the forward rate constant greater than or less than or equal to the reverse rate constant? Go back, let's go. So which K should be, yes? K forward larger than K reverse. Yes, I agree. So everyone see why? It's going to, the rate for the reverse reaction going this way is going to be slower because we have the larger activation energy to overcome. Cool. All right, this slide is just kind of a summary of what we've been talking about. I've also included a figure for an endothermic reaction with an activation energy. So the activation energy for the forward reaction is greater than that for the reverse reaction. Okay. Yeah, this kind of just summarizes the last few things. So I'm just going to let you take a look at that later when you're going over your notes. Here's another quick question for you. Which rate constant is larger, A to B or C to D? Similar question. These are supposed to be hills. A to B is larger, yep. Good. Cool. Okay, so we're going to work on a 2-point Arrhenius equation problem. So this says that, I'm just going to go ahead and show you the Arrhenius equation and our temperature. So a reaction is studied at different temperatures and the rate constant K is calculated. The rate increases as the temperature increases, as we would expect. It says that the rate doubles when the temperature is increased from 20 degrees Celsius to 60 degrees Celsius. And I want to know what is the energy of activation. Yes?
So when I was doing the homework yesterday, I did one of these problems, and the right answer ended up being the 1 over T1 minus 1 over T2, not 1 over T2 minus 1 over T1. So I don't know, I'm just confused on that.
Okay, so you're saying that they gave you an equation that has T1 minus T2?
Well, yes, that was the equation I was supposed. So I did it originally this way, but Matt told me I was wrong, so I did it opposite.
I think if you do that, it's fine as long as you also flip the rate constants.
Okay. Yeah. Oh yeah, yeah. I see. Okay, I see it.
Yeah. Yep. Okay. So important things for this type of problem to remember is that R is 8.314 joules per mole Kelvin. And because it's Kelvin, we need to make sure that our temperatures are in Kelvin. And I've gone ahead and calculated those for you. I'm going to have you work on this for a few minutes. See if you can come up with an answer. This one's a little bit trickier than some of the others. Yes? Oh, you're right. Yep, you're right. There's a typo. Let me see what I did. So, can we change this to 40 here? That makes things easier for me. All right, so take a few minutes, work on this one. Let me know what you get if you have questions. What are you using for K1 and K2? 1 and 2. Why is that? It doubles. It says that the rate doubles when the temperature is increased. So K2 equals 2 times K1. Oops. Okay. Does everyone see that? Questions on that?
You just assume if they don't give you a grade because it's
Yeah, so the question is, what do you do if they don't give you a rate that says it doubles or something like that? Set up an equation that's describing that. If it said that the rate is tripled, K2 equals 3 times K1. If the rate is half K2 equals 1/2 K1. Something like that. So I'll set up the rest of the equation, give you the right answer, and I'll make sure you can do the math for it. So I had ln of K1 over 2 times K1, because K2 equals 2 times K1, equals E sub A over 8.314 joules per mole Kelvin times 1 over 313, I'm leaving off my decimal, it's fine, 1 over 293. And so when I go and calculate E sub A, I got 26500, we'll round up. And this is joules per mole. Many times you'll see the activation energy given in kilojoules per mole. And that's about the right order of magnitude that you should be expecting. Make sure that your your gas constant R and your units on activation energy are matching up. So if you're given an activation energy of 26.5 kilojoules per mole, either convert that to joules or make your rate constant in kilojoules, or your gas constant in kilojoules. Okay? Questions on this problem? Okay. All right.